I get done. Okay, I feel confident enough that I'm just going to start with this. This is now looking at the angle between two vectors, and we use the dot product and the magnitude to find that angle. So here's a pictorial representation of an angle. Vector u is going out that way, vector v is going this way. The angle theta between them is right there, and then this vector can be considered v minus u as we've looked at things. So I'm just going to get rid of that writing, and the angle between two vectors, and notice that that angle is given as 0 is less than or equal to theta, which is less than or equal to pi. So we're going to have a maximum of 180 degrees or pi radians. And the angle can be found using the dot product. So this is something you want to write down as we go through this chapter. The angle between two vectors, if theta is the angle between two non-zero vectors, vector u and vector v, then the cosine of theta is u dot v over the magnitude of u times the magnitude of v. And so, you know, if we write it, cosine theta is u dot v over the magnitude of u. Oh, okay. The magnitude of u times the magnitude of v. Kind of writing it in our longhand way. And our first picture has the picture drawn as well. So here's our job is to find the angle theta between vector u, which is 4, 3, and vector v, which is 3, 5. You might have noticed they're picking kind of easy to work with numbers a little bit there. And these are put in standard position, so they're each starting at the origin, and then one goes 3 to the right, 5 up. The other one goes 4 to the right and 3 up. So that angle that we want to find is just in between those two. So the cosine of theta is u dot v over the magnitude of u times the magnitude of v. And so I think on the side, I'll just kind of figure all those things out. So u dot v is going to be 4 times 3 plus 3 times 5. And what is that? 12 plus 15, so 27. So that's 27, and then the magnitude of u is the square root of 4 squared plus 3 squared. So 16 and 9, so it's the square root of 25, or 5. And then the magnitude of v is the square root of 3 squared plus 5 squared. This one isn't quite as handy. 9 plus 25, so it's the square root of 34. And I don't even think we can put that in simple radical form. It's just, it is what it is. So then the cosine of theta is 27 over 5, the square root of 34. Now, do I have to rationalize that denominator? Not necessarily, because I just want to find theta. So theta is the inverse cosine of 27 over 5, the square root of 34. And, you know, because I'm just using that to manipulate my stuff, I'm good to go. And we'll give that in radians. So if your calculator is in radians and you type that in, you get theta is approximately 0.3869 radians. And I'll just write that. Now, sometimes you can find that angle in degrees as well. And so that's just another version of what you have to do there. I think I'd like to have you try one of these. And so here's the problem, and we'll call this 3b. If u is 2, 1, and v is 1, 3, I want the angle between u and v, and I want it in degrees. So take a minute, that'll kind of warm you up to, practicing, practicing some vector things. So take a few minutes and just find the angle of u or the angle between u and v in degrees. What did you get? 45 degrees. How many people got 45 degrees? So we kind of see. Okay, good. It is 45 degrees. I'll just write parts of the answers. U dot V, am I right in saying that's 5? The magnitude of U is the square root of 5, and the magnitude of V is the square root of 10. So theta is the inverse cosine of 5 over the square root of 5 times the square root of 10. And that should kind of all work out for you. Now, the next thing we want to do is we want to think about this formula a moment. Oops, and I'll kind of go through there. There we go. We want to think about this formula, and I'm just going to write it again. Cosine theta equals u dot v over the magnitude of u times the magnitude of v. So when you look at this, if we wanted to multiply both sides by the norm of u and the norm of v, which is kind of a lot of writing, multiply by the norm of u and the norm of v, so if I multiply that, what I get is, and I'm going to just kind of reflect that across the axis, or the equal sign, I get that u dot v is equal to the norm of u, or the magnitude of u times the magnitude of v. And I don't know, for some reason my u's and v's are looking very alike today, cosine theta. So I want you to notice that we can use that formula that we used to find the angle, but we can rearrange it and we can write it as an alternate form of the dot product. Does that make sense? So there's another form of the dot product. Not only that, we can say this, look at this. And when I say look at this, I'll kind of point with this. That has to be positive. Do we agree? And this has to be positive, correct? So the sign of the dot product and the cosine of the angle have to be the same. Do you agree with that? So if the cosine of the angle is negative, then the dot product will also be negative as we look at that. So that's something to kind of think about or contemplate. And I want you to think about a 90-degree angle a moment. What is the cosine of 90? 0. So what's the dot product if the vectors make a 90-degree angle? It has to be 0. Does that make sense? So and I'll just write a little note. If theta is 90 degrees, then the cosine of 90 is equal to 0. So u dot v would be equal to 0. And so if the vectors are perpendicular, 90-degree angle, they make a 90-degree angle, then their dot product is going to be equal to 0. And that's actually on a slide here, but I like to kind of talk about it a little bit before you see that. So here's that thing we just talked about, an alternate form of the dot product, and sort of talking about the cosine of theta and the dot product have the same sign. And then just here's a bunch of pictures. And, I don't know that you need to write them down, but here's some orientations of two vectors. We can have them, the angle be theta, where they make 180 degrees or a straight line. They're opposite angles. We can have that cosine be a negative between -1 and 0. We just talked about this one where the cosine of that angle is 0, so then the angle is pi/2 or 90 degrees. We can have an angle between 0 and pi/2, and then our cosine is a positive between 0 and 1. And we can have it so vector v and vector u are in the exact same direction, and so our angle would be considered 0 and our cosine would be equal to 1. So those are just kind of the 5 ways that these angles can be oriented. And let's see, physics students, do you know the name of when vectors are perpendicular? I don't know. Have you used a word for that? Okay, well, you can tell me if you recognize it when you see it. The word is orthogonal. Oh, no and yes. Okay, so this is the definition of orthogonal vectors. And so orthogonal vectors, so here's a nice little sentence below there. Orthogonal and a perpendicular essentially mean the same thing, meeting at right angles. So the definition of orthogonal vectors is if their dot product is 0, they're orthogonal. If they're orthogonal, then their dot product is 0. And so we can check if things are orthogonal by finding their dot product. So that's our next problem. Are you ready for me to go ahead? No. Okay, and then just here's a little straightforward example. Are vectors u and v orthogonal? So to see if they're orthogonal, we're going to find their dot product, and if it's equal to 0, then we're going to say yes, and if it's not equal to 0, we'll say no. So the dot product is 2 times 6 plus -3 times 4, and 12 minus 12 is 0. So yes, they are orthogonal. And when I did this, I also plotted them. If you're uncertain or you ever want to validate something like that, using a a graph, that's always kind of a good idea. So if I put those with the origin as the initial point, 2, -3, 1, 2, 3 is right there. And I'll draw it freehand. And then 6, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 is right there. And, you know, visually they kind of look like they make a right angle there as we go through it. So just to kind of validate that if we need to. Now we want to talk about vector components. So finding vector components is our next little section here. And that's what I want to kind of look at today a little bit more. So you have seen applications in which vectors are added to get the resultant vector, and a lot of things in physics and engineering may have the reverse problem, is decomposing a vector into the sum of two vector components. So, and here's this little boat problem that we had looked at earlier in a different section. So now consider the boat on an incline ramp, and the force due to gravity pulls the boat down and against the ramp. And so W1 and W2 are going to be kind of the components. These two vectors add to be kind of that force that's going straight down. And so these two, and they're orthogonal. These two orthogonal forces, W1 and W2, are the vector components of F. And maybe I'll just kind of write that on this picture, so, or by this picture, so we can kind of see that. So F is equal to W1 plus W2. And W1 and W2 are orthogonal. So W1 and W2 are orthogonal. And then we can also say that the negative component of W1 is the force needed to keep the boat from going down the ramp, and the W2 is the force that the tires have to withstand against the ramp, kind of pushing against the ramp as we look at that. So now we need a procedure for finding W1 and W2. And we have a picture for that. So here it is. This is the procedure for finding W1 and W2. So this is when theta is acute. It might look like this. And so that's kind of that easier to visualize picture. And then if theta is obtuse, it just kind of looks a little bit different in our orientation as we go through. So it's like kind of having a triangle and thinking of that altitude that could be in or outside of the triangle. So the definition is, let U and V be two non-zero vectors such that U is equal to W1 plus W2, where W1 and W2 are orthogonal and W1 is parallel to or a scalar multiple of V, as shown in this figure right here. Bless you. The vectors W1 and W2 are called the vector components of U, and vector W1 is the projection of U onto V. So it's the projection of U onto V, and W1 is written as the projection, abbreviated PROJ, subscripted V, and then a U next to it. So W1 is the projection of U onto V. And the vector W2 is just U minus W1. U minus W1. So the book authors kind of go through a little process of how you can find that projection. And so I'm just going to kind of read through that. I think it's a good thing to look at. And then what we really want to write down is a formula kind of looking expression for how to actually find this projection thing. And I think you'll find it's pretty straightforward to actually do it. So here's our book authors kind of putting this all together. So you know that U is equal to W1 plus W2. And you know also that W1 is a scalar multiple of V. And we were kind of told that so that we can convert the W1 or change it, substitute it with C times V. And then we're going to take the dot product of each side with V. So we're just going to take this U and dot with V, and then this kind of whole piece and find the dot product with V. And when we do that, we know that that dot product of U dot V can be CV, that scalar C times V dotted with V plus W2 dotted with V, because that dot product is kind of, we can use that distributive property. So we get this. And what could we reconsider V times V as? The magnitude of V squared, and so we can think of it as that magnitude of V squared. And what is true about W2 times V? Let's look at that picture here. Here's W2 and here's V. What's true about their dot products? What should their dot product of these two be? How are these two vectors related? It should be 0 because they're orthogonal. W2 and V are orthogonal, and here they are here as well, still orthogonal. So W2 and V are orthogonal. So their dot product, let me just kind of get rid of that writing a minute. Their dot product should equal 0. So then when we go back to this slide we were just looking at, oops, there we go. W2 times, or dot V should be equal to what? 0 then. And so we can say this is U dot V equals, remember we have in our properties that if we take V dot V, it's the same as the norm of V squared plus 0. So we can kind of do some substituting right there. And I want to get C alone. If I want to get C alone, I'm going to divide by the magnitude of V squared. So U dot V equals the magnitude of V squared, or excuse me, divided by the magnitude of V squared is equal to C. And then I can kind of flip that. Here's our next slide from the book authors. So we just talked about that is 0 and this, and then we get C this way. And so from that little property from before, W1 is the projection of U onto V. And that's equal to C times V. And so then we can turn it into this. And then that is our new property, or our new, way of finding if v and u are non-zero vectors, then the projection of u onto v is given by this this little formula. So the projection of u onto v is equal to u dot v over the magnitude of v squared all times. And I have to always be careful. I sometimes want to write a time sign, and that's a bad idea with all the dot products that we're doing. So we're going to do example 5, which is using this projection kind of method of doing things, and then we'll kind of be done with our new notes for today. Are you ready for me to move on? Yep. Okay, so this is number 5, and it says find the projection of u, which is 3, -5, onto v, which is 6, 2. So that's going to be using that formula, and then write u as the sum of two orthogonal vectors, one of which is that projection vector. So the first thing we want to do is find, we'll call it W1, which is the projection of u on v. And so then we'll just write that formula, u So there's our formula, and maybe again to the side I'll find some of those things that I'm going to need. So u dot v is 3 times 6 plus -5 times 2, and that's 18 minus 10, so that's 8 for the dot product. And then the magnitude of v is the square root of 6 squared plus 2 squared, 36 plus 4, it's the square root of 40. Oh, and I have an error in my formula, don't I? In my formula, I really want to square it, because I was just going to ask, do I need to rationalize this? Not at all. And I probably don't want to rationalize it because I'm going to square it in just a moment. So I'm kind of good to go. So that's going to mean that this is 8 over the square root of 40 squared times v, which is my 602. And so that's 8 over 40. And what's 8 over 40? 1/5. So it's 1/5 times 6/2. And so that's 6/5 and 2/5. So that's our first part of our answer, is just finding the projection of u onto v. Then we have to write u as the sum of two orthogonal vectors, one of which is this vector that we have here. And so I'm sorry, the other component, I forgot to do the other component. The other component, W2, is kind of easy to find relatively, is W2 is U minus W1. And so now we'll just take, and I'm going to just write that again here. W2 is U minus W1. And so U is, U is the 3, -5. And minus W1, which was right here, is 6/5, 2/5. So we have to get a common denominator. I actually will write it with a common denominator real quick. 3 is how many fifths? 15/5. So I have 15/5, and 5 is how many fifths? 25/5. And then I'm subtracting 6/5 and 2/5. So W2 is 15 minus 6, which is 9/5. And -25, it'll turn out to be plus 2 is what? -23/5. Did I make a mistake here? Oh, it must be, yes. Yep, I did make a mistake there. So yes, it should be a comma instead of a negative sign. So that kind of changes things there. Comma, and then -25 plus 2 is what? -23/5. Oh my gosh, wow. It is -27. -25/5 minus 2/5 is -27/5. And that's a comma in there. Ooh. Okay, and that is what I have written on my paper, and that is actually correct now. Yay. And so if we want to find U, then U is, or kind of, check that U, and that is W1 plus W2. And so W1 is there, right? And plus W2 is there. So that means that W1 is 6/5 and 2/5 plus W2, which is 9/5 and -27/5. And so what is that? What's 9 plus 6? 15/5, which is what? 3. And what's 2/5 minus 27/5? -25/5, which is what? 5, or -5. And what did I just do? I just am checking my work, right? And so I want to kind of make sure that that all works out. And what should be true about W1 and W2? They should have a dot product of 0. So if I find W1 dot W2, I'm going to have 6/5, 2/5 dotted with 9/5, -27/5. And that'll be, oops, equals. What's 6 times 9? 54 over 25. And what's 27, -27 times 2? Minus 54 over 25. So they are indeed orthogonal, just to kind of have a little extra check there. And then I will just show this next 2 pages. There's kind of some work written there. And then here's the pictorial view of that. And so you can kind of look at that. I'm going to stop at 5. Just a reminder, 6-3 homework check is tomorrow. And then you can use a little bit of time, I guess, to work on things.